Hi, I'm Ben-Yaakov. This presentation is entitled Answers to Analog Riddle, Part 2, Heater Resistance and Distortion. This is part of the answers to a riddle that I have posted earlier in my YouTube channel. This is the link to it. And there is a part 1, and this is the link to it. The riddle was related to a description of a project that is described here and posted at the Altium website, and also here is the link to it. I'm going to put the 3 links in the page of this YouTube video so you can click and get to them. So let me go first of all to describe the project in general and go into the second part of the answers. So this is the description of the project, current transformers, how to project, posted on January 20th this year. And my question was related to the content of this description. The first part of the answer covered 2 issues, the current transformer and description or design of the precision rectifier. Now here I'm going to address some of the rest of the questions that I've posed on this description of the project. So here's the first one, point 1. In the description of the project we read the following: a rough estimate of current should be determined by reading just the peak voltage, but to get an accurate current measurement you will need to take many measurements to determine the total area under the curve, that is the current draw. Well, total area is giving you average current, which is not of interest. In fact, you'd like to get the RMS, and for that you have to take a sample and then take the square of the value and then sum all the squares. So just taking the total area under the curve is just of no interest as a matter of fact. So let's move now to the second point. In the description it says, note how the waveform is not as perfect as the function generators. Real world loads are almost never going to be perfect sine wave. This statement is related to this scope output, which is an output of a function generator and then a shifted value of it with a DC bias, and then an actual current measurement of a heater that was, the current was fed to a current transformer, and this is the output of the current transformer. So again, the statement is, note how the waveform is not as perfect as the function generators. Real world loads are almost never going to be perfect sine wave. Okay? So the clamping here is attributed to the load, to the heater, and it says that, well, real loads are not always like a function generator output sinusoidal waveform. Well, this is wrong, because this clamping are due to the fact that the line voltage is distorted. It has nothing to do with the load. In this case, the load was fed from the line, and the distorted waveform is due to the shape of the power line voltage. It has nothing to do with the load. A clamped voltage is typical in most power outlets. It is due to loads with rectifiers and simple capacitive filters, and these cause heavy current at the peak voltage, which attenuates it, and it is very typical to see a voltage coming out of the outlet or the line that is really clamped like this. So the reason why the current is seen like this clamped is not because of the load, but rather because of the voltage feeding the load, and therefore you see a reflection of the voltage, because the current, of course, is voltage over resistance. And the resistance is changing, but not at a rate of the line. We'll talk about it a little bit later. So this is point number 2. So let's move to point number 3. Here it is. It says, despite how amazing, accurate op amplifier tuning in these days, or turning, having both amps in the same package greatly increases the likelihood of the same gain being applied by both amplifiers, which is important. In my final design, I'll also be using 0.1% resistor for the same reason. Well, the gain, the open loop gain of an operational amplifier has little and really insignificant effect of the closed loop. This is the beauty of operational amplifier. The open loop gain can change a lot, 10%, while the closed loop will change very little. That's basics of feedback theory. So saying that because of the two amplifiers are the same package, and then they'll have the same gain, and this will cause the same output in closed loop, is just incorrect. Perhaps having the two amplifiers, the same package, will do some matching of the that should be voltage offsets, and perhaps bias currents, and certainly temperature will be equal for the two units, but has nothing to do with the gain of the amplifier. The gain can change quite a bit in open loop, and you'll see very little effect in closed loop. Okay, so then we come to point 5. It says, finally, I have a simple 600 Hertz RC filter at the output of the op amplifier to remove any AC. Now, let me just very briefly go over this point, which is discussed in part 1 of the answer. Well, here it is. This is the filter we're talking about now, and this is supposed to be 600 Hertz, but as I'm discussing it in part 1, because of the diode, this is now becoming a nonlinear filter. While the amplifier is feeding the current, you have here low impedance, while when the capacitor is discharging, it's going this way, and therefore it has a different time constant, and this is causing distortion. So this is a very poor filter, and it is distorting the waveform, and in fact you can see it. Here it is. This is the output of the rectifier, and you see that this distortion, and this is due to the fact that the filter is nonlinear. I'm discussing this in part 1. And then we come to point 7. Notice the negative wave is a little lower in voltage than the positive one. That's because the resistors I'm using are not practically well matched. Okay? Now we are referring now, this is the output of the rectifier. This is the input coming from a function generator, which I would assume is sort of replacing the current transformer. And here we see a difference here. And it is attributed here to the fact that resistors are not well matched. On the other hand, in the real measurement of the real current, this is now the current of a heater going through the primary of the transformer, and this is now the current, and this is the rectified value. We see that there is no difference here. In fact, the magnitude here is actually even lower than the magnitude here, so you can't say it's a matter of here maybe clamping. And so how come that in this case the resistors, which are not apparently matched, are causing this difference, while in this case they don't? Just doesn't make sense. Either they affect the accuracy, and then you expect to see here also the same difference, because you're using the same resistor and the signal goes through the same path. Now I would suspect that the reason for this asymmetry has to do with the fact that rather than having the voltage coming out of the current transformer, it's now coming out of the function generator. This is the output of the function generator, and not from the current transformer. Now, as I've shown in part 1, and let me go back for a second to the slide of the part 1 answers. So here it is. This is the rectifier, this is the source, and now we're talking about the following situation. In one case, current is coming in, a voltage is developing here, and then we see the output. Case number 2, this is apparently was replaced by a function generator. Okay, so this is the first case. In the case of the function generator, the output was not symmetrical. We saw asymmetry between the two halfways. Now, as I've discussed in the first part of the answer, the gain here, this is now an inverting. For the negative part of the cycle, this is an inverting amplifier. Now, the gain here depends on the resistance here and the resistance here, this resistance times the resistance, but contrary to intuition perhaps, this is not the ratio of these two resistors, but really you have to take into account that this is a current source, so this is representing Thevenin voltage source of this. So in fact you have now a resistance which is this plus this. Okay, this is this. So there is an error in this case of say 1%. Now, if the function generator put here had an output resistance of say a couple of hundred ohms, I don't know what the setup was, then it would cause a lower gain in this path. While in the path of the positive, in the positive case, when the signal is positive, this amplifier doesn't work. We have the signal coming here directly to here, and then it's going out. So an error in the ratio here will corrupt only the negative part and not the positive part. And so an internal resistance of the source can explain what we are seeing. So let's go back to it. So here it is. You see that this one is lower, and this is the negative part. So this is consistent with the explanation that I'm offering. I don't know if this is the only explanation, if this is the right explanation, but this is certainly a possible explanation why you see this asymmetry when you're feeding a signal generator, and this would be due to the internal resistance or the output resistance of this function generator, while in this case the output is coming from the current transformer. There is an error, but in this case the error is very small, so this is why you see it just about the same. So therefore, I think that just saying that as we test this with the heating element as a load, the error is not as noticeable. Well, it is not noticeable for a reason, and doesn't say why. And I think again, matching of the resistors and the mismatch of resistors does not explain this, because here we have it, and with the same resistors, we don't have it. So this is point 8. So let's move now to point 9. And in point 9, it says the following. I used a 4-wire resistance measurement to measure the heating element. After letting my multimeter average the reading of for a while, it settled at 50 ohms. Okay, what's the purpose of measuring this resistance? The purpose is to estimate the correct current at the heating element, because let's go over here. It says the resistance was measured to be 50 ohm. The line was measured to be 239.6 volt. So therefore, the current should have been 4.7 amp, while the rectifier showed a 4.4 RMS. Okay, and the conclusion here that there's a mismatch, is a 7% error. Okay, so let's go back here. The measurement was made of the heating element while it is cold. Now, as we know, every conductor is temperature sensitive, and let's assume that the heating element is tungsten. It probably is. Here we see the resistivity of tungsten as a function of temperature. This is in Kelvin. So when it is cold, here it is. Now obviously, when current is passing through the heating element, it's getting hot, it's moving up to a higher temperature. And as you can see, as the temperature goes up, the resistivity goes up, and therefore the resistance will go up. So going back now to the conclusion here, just dividing the voltage by the resistance at room temperature does not give you the current when the heating element is hot. And therefore, all this conclusion is just incorrect. That's a big mistake. And then it says that you can buy more precision current transformers, and so that he's sort of attributing the error to the current transformer. Obviously, it's not. Current transformers are pretty accurate because it primarily depend on the turns ratio, and you can't be off by that much. And so this 7% is obviously due to the fact that the resistance of the heating element is higher, and this is consistent here. You see, calculating it from the cold heater, it's 4.7, and the actual measurement is 4.4, which makes sense because the heater was getting hot. So this is also a very big mistake here. So let's move now to the last point, which is point 12. And the question was, what would be a better rectifier circuit? Well, I'm not going to cover it in this video. It's going to be detailed and discussed in a forthcoming video, in which I'll also show different type of rectifier topology. So this brings me to the end of this presentation. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.